let's talk a little bit about unidirectional link detection. This is a Cisco proprietary protocol. You might hear a lot of people call it UDLD because that's what most network engineers will refer to when talking about it. But what we're trying to do with this protocol is detect if a link is either bidirectional or unidirectional. A lot of times that, if a link goes unidirectional, i.e., maybe one strand in a pair of fiber strands goes dead, I know, far-fetched, right? But it could happen. What we'll see is that the physical link state will actually remain up, all right? So we won't be able to detect a failure at the physical link level. So what happens is we depend upon those upper layer protocols like spanning tree, OSPF, EIGRP, and their internal timers to detect that, hey, yeah, we've lost a peer across this link. So a typical scenario people may throw at you, let's go over here to the whiteboard, is imagine if we had two switches. So we'll have switch 1 here, and we'll draw switch 2 over here. So let's take a link out here. And imagine this is just one big port. So we have, two fiber strands, guys transmitting here, receiving here, guys transmitting here, and receiving here. So what could happen, and I know it's far-fetched, but what could happen is we could lose a portion of this link. So we could lose, the transmit on switch 1 side, i.e. the receive on switch 2 side. So really the only frames that are going to be coming in are going to be sent over here from switch 2 towards switch 1. Okay? So again, the physical link state may remain up in this specific case. Again, what we would be depending on would be things like EIGRP or spanning tree timers. We'd be waiting for those to basically expire because the only frames that would be getting through, or packets, would be coming from switch 2 to switch 1. So sooner or later we would have some timeouts and the upper layer protocols would have to actually converge in order for traffic to basically flow again. So we needed something to kind of fill this void because we can't quite depend on layer 1. At layer 1 we're going to have things like auto negotiation taking place. But we don't have any upper layer protocols kind of trying to detect if that link is in fact bidirectional. So that's why Cisco actually came up with UDLD. So what UDLD, let me go back to my PowerPoint here, what UDLD is going to allow us to do is run a protocol on top of layer 1 because it kind of operates at layer 1, layer 2. We're going to be sending these small frames across this link, and I've actually placed the MAC address that UDLD uses right here. So we're going to form a neighbor adjacency with the remote side, and we're going to start sending frames to this MAC address. Now what we're actually going to be doing is putting our device ID in there along with an outgoing port ID, and if we see that frame echoed back to us across that link, we know the link is bidirectional. Okay, we're going to receive the frame, we're going to see our outgoing port ID. Within that frame, we're going to know everything's groovy across that link. So using this method, we can detect that that link is bidirectional. Now, what happens if we start missing one of these frames? Well, we're going to be sending these guys about every 15 seconds by default. Okay, every 15 seconds by default. So if we miss one, it might go into an undetermined state. All right. Once we miss three once we miss three coming back to us, we're actually going to declare that link as unidirectional, and we're going to put that dude in error disabled mode. So nothing big there, right? So total convergence time, if you do 15 times 3, that's about 45 seconds until we put that port, or ports, I should say, because it's between two switches, into an error disabled state. What that'll do is allow those upper layer protocols to go ahead and converge, maybe a little bit quicker than they would with their standard timers. The real goal with the initial implementation of UDLD was that 45 seconds was a little bit less than 50 seconds. Okay, so what that would allow us to do is go ahead and error disable that link before maybe a loop condition kicked in the network. So you guys know about loop guard, right? So if we had, two switches here, and let's say neither of these guys are the root bridge, but on this specific link, one is going to be the designated forwarder, and the other might be blocking. Again, that's going to be determined within the BPDUs. So what's going to happen is this guy's going to be pushing BPDUs across. If the spanning tree process were to fail on this switch, okay, if the spanning tree process were to fail on this switch, what would happen is this guy would go ahead and adjust his port, and he may start forwarding on this link. Well, if this spanning tree process was what was in fact broken, he might still be forwarding on this link as well, and all of a sudden we have a loop condition. This is where loop guard would kick in. If we had loop guard configured on this blocking port, it would detect this and go into like a loop inconsistent state. But what we're trying to do is time out this unidirectional link before something like this can actually occur. Okay, we don't want to both be flooding that link with information, so if we can detect that using an L1, L2 protocol, kind of like UDLD, before spanning tree kicks in and says, oh yeah, I need to start forwarding across this link, all the better, right? So really UDLD serves this purpose, and it serves it very well. But 45 seconds for a lot of things is a little bit too slow. So by default, UDLD is going to run in one of two modes, and when we first enable it, it's going to run in what we call normal mode. And the kind of actions that I've talked about prior to this have all been discussing in normal mode, because when we enable UDLD, that is the default. What we can do is we can actually put it in a different mode that's called aggressive. Now what aggressive mode is going to do, as soon as it loses that first frame, okay, so we're not going to wait for 3, we're still sending out every 15 seconds. Once we miss that first one, what we'll try to do is we'll send 8 frames out, okay, 1 every second for 8 seconds. Try to reestablish the neighbor adjacency. I tell people, we're trying to aggressively reestablish that neighbor adjacency with that remote end. If we don't get any of those back, we're going to go ahead and just error disable the port. So rather than waiting that whole 45 seconds, we get the benefit of, you figure 15 plus 8, that's almost a half reduction in time in order to bring that link into an error disabled state. So basically 15 seconds, we miss a frame, we send out 8 in succession every second trying to reestablish that neighbor adjacency. If we don't get anything back, boom, link goes down, upper layer protocols can go ahead and converge. So again, aggressive mode is probably the better option in terms of UDLD. Now, when we get in and configure UDLD, I'm going to show you guys how simple it is to configure. Really, all we're going to do is we're going to come in and we're going to turn on the feature UDLD. Once we do this, UDLD is going to be enabled for all 10 gig fiber optic ports on these NXOS-based switches. Every single one of them. What it won't be enabled on is copper ports or twin-ax ports. So if we want to enable it under the copper or twin-ax ports, we have to manually go into that port and say UDLD enable. Okay? And to turn on UDLD aggressive mode, again, it's going to be a global configuration option. All we're going to do is go in and say UDLD aggressive.